Hello everyone. So today let's solve the problem Andrew and the chemistry, right? So this was asked in the Codeforces around 373 for the rated for the division 1. So I can just go through the question. It's easier to understand. I'll just summarize the question so that it will be easier for us to solve the problem. Yeah, just give me a second. 1 second. Yep. So yeah. So what the question states here, we are given a tree with n vertices. Yeah. So we are given a tree with n vertices, meaning degree of each vertex has to be less than or equal to 4. Yeah. So we have been given a tree with n vertices. Degree of each vertex has to be less than or equal to 4. So we have to count how many distinct non-isomorphic trees can be obtained. Yeah. So we have to count how many this one non-isomorphic trees non-isomorphic trees can be obtained by adding one new vertex by adding one new vertex. Yeah, so just give me a second here. By adding one new vertex. Yep. So given a tree with the n vertices, degree of each vertex less than or equal to 4, we have to count how many distinct non-isomorphic trees can be obtained by adding one new vertex and one new edge. One new vertex and one new edge actually. Yeah. So this is fine, I believe. So that the result is still a tree and every vertex degree is less than or equal to 4. Every vertex degree is less than or equal to 4. Yeah. So two resulting trees are considered the same. See here, two resulting trees are considered the same if there is a graph isomorphism between them. If there is a graph isomorphism between them. Yeah. So we have to output the number of distinct isomorphism. We have to output the uh, number of this one distinct isomorphism. Yeah, we have to output the number of distinct isomorphism. Yeah, this one isomorphism classes obtained by this one attaching the new leaf to any vertex with a degree less than. Yep. So this is the question actually. So let me read this one out loud again. Just listen to this carefully. We have been given a tree with n vertices. Yeah, and degree of each vertex has to be less than or equal to 4. So we have to count how many distinct non-isomorphic trees can be obtained by adding one new vertex and one new edge. So the result is still a tree and every vertex degree is less than or equal to 4. Every vertex degree is less than or equal to 4. Two resulting trees are considered the same. Two resulting trees are considered the same if there is a graph isomorphism between them. If there is a graph isomorphism between them. So what we need to output here, we need to output the number of distinct isomorphism classes obtained by attaching the new leaf, right, to any vertex with a degree less than 4. With the degree less than 4. Basically, we need to output the number of distinct isomorphism classes, yeah, in simple terms, that is obtainable by attaching the new leaf to any vertex with degree less than 4. So this is the question actually. Yep. So this is the question. So we have been given number of nodes here. We can clearly see here 1, 2, 3, 4. We have 4 nodes here. N is 4, and we have been given edges here. So the number of distinct isomorphism classes here is nothing but the 2. Same goes with the input 2 as well as the input 3 as well. Yep. So, yep. This is about the question and the input output part. Man, let's do one thing. As we are completely familiar with the question as well as the input output part, let's discuss the approach followed by the complexities and then let's write the code. Yeah, as usual. First, let's discuss the approach part actually. So I have considered the same first example that they have given in the question, right? So n we have been given 4 and this one, these are nothing but the edges, right? So this is fine. Now the output that we need to get here is 4. And one more thing, before moving on with a step-by-step explanation. So we will be going with a tree hashing approach to solve this particular problem. Yeah, just remember this. We will be going with a tree hashing approach. Let's move on with a step-by-step explanation here. So this is fine. This is the input that I have considered. See, here uh, the I have drawn the graph accordingly with the input. Say 1 to 2, these are the edges, right? 1 to 2, this is one thing. 2 to 3, this is one thing, and 2 to 4 is one thing. So this is fine. 2 to 4, yeah. 1 to 2, 2 to 3. So this one, and 3 to 4, 2 to 4 actually. So 1 to 3 we don't have, right? So let me do one thing. One second. Let me delete this one. This is not required actually. Yeah. One second. Yeah, this is fine. Yeah, so this is the graph actually. See, by looking at it, we can tell that. So this one, vertex 2, sorry. Uh, yep. This one actually. One second. So vertex 2 here is the center, right? So by looking at it itself, we can say here, see this one, vertex 2 is the center, nothing but the with the degree 2, with the degree 3 actually, it is going to 4, 2 to 4, 2 to 1, as well as the 2 to 3, right? So vertex 2 is the center with the degree 3 that is connected to the leaves 1, 3, 4 respectively. That is connected to the leaf. See here, 1, it is also connected to 3, it is also connected to the 4. So vertex 2 is the center here, right? So this we know, this is fine. Let's move on with the this one, main core logic here. So what we'll be doing, let's try to understand now. We have seen the graph actually. So vertex 2 is the center. Now we know for every vertex v, for every vertex v, there are four vertices, right? So total 1, 2, 3, 4. For every vertex v whose degree less than 4, we may attach a new leaf to the v, right? So new leaf to the v. So every vertex is less than 4 actually. Every vertex has a degree less than 4 actually. 2 consists of the vertex 3, and all other this one, 1, 3, and 4 is having the degree 1 actually. The only vertex actually 2 which has the degree 3 actually. So every vertex is having the degree less than 4. For every vertex v whose degree less than 4, we may attach a new leaf to the v. So this is the criteria in the question. They have already mentioned in the question. Attaching it attaching to different vertices may give isomorphic or the non-isomorphic trees. Yeah, attaching to different vertices may give isomorphic or non-isomorphic trees. So this is fine. Yep, let's move on with the next part. Now we have the idea. Let's move on with the next part. So to detect the isomorphism, this one efficiently, we will calculate a canonical rooted. See, we will calculate a canonical rooted encoding of the tree. So we'll be calculating canonical rooted encoding of the tree, basically to detect the isomorphism efficiently, right? So when rooted at each candidate vertex, identical encodings means this one. Identical encodings means isomorphic, right? Isomorphic results after attaching a leaf to that particular. This is fine. Now let's move on with the third part here in the example that we have considered. So attaching to the center vertex 2 gives a 4-leaf star. So basically 2 is having the degree 3, all other vertex 1 as well as the 3 and 4, right? So all other vertex is having the degree 1, right? So we know this one. One second, just give me a second here. Yeah, 1, 3 and 4 is having the degree 1, 1, 1 respectively. Yeah. So this one, attaching a new leaf to the this one center vertex 2 gives a 4-leaf star. So it is 2 is already having 3. So one leaf if we attach, so this will give the 4-leaf star. So this is fine. Attaching to any leaf 1, 3, 4 gives the same shape. So this one will be 1 plus 1. If we attach this one, this will give 2 actually, same shape, right? So there are two distinct encodings. So answer is 2. So there are two distinct encodings here. One is attaching to this one, 2 actually, the center node actually, or the center vertex will give us the 4, right? 4-leaf star, and attaching to 1, 3, 4 will get 2, same shape, right? So this one we have, there are two distinct encodings here. In this case, answer is nothing but we have to return, or we have to display the distinct encodings itself, right? So here in this case we have the answer 2. So this is 1 and this is 1, this one encoding, right? So this will be, there are two distinct encodings, basically answer is 2. So the output that we got here is 2, which is equivalent to the output that they have mentioned for the, just give me a second here. So what they have mentioned for the example 1 within the question. So here I have written wrong. We have to get the output 2. Sorry, we shouldn't get the output 4. So yeah, in the question they have mentioned 2 itself. By mistake I have written 4 here. This is fine. Let's change this one. The output that we need to get here is 4. So the output that we got here is 2, which is equivalent to the output that they have shown for the example 1 within the question. So our approach works absolutely correct here. So as we are completely familiar with the approach, let's do one thing. Let's quickly discuss the complexities part. Yeah, let's quickly discuss the complexities part. So what will be the time complexity here? The time complexity would be big of n. Why it is big of n here? Each directed edge node comma parent is processed exactly once. Yeah, so sorting per node is over less than or equal to 4 children, so constant time per node. So it will be constant time per node, so overall time complexity would lead to big of n. So what will be the space complexity here? Space complexity would lead to big of n, because we will be going with the adjacency lists as well as the memoization maps and also the recursion stack, right? We know that this one, the recursion stack, the depth of the recursion stack can take up to the big of n, right? So overall space complexity would lead to big of n. So the time complexity and the space complexity for the code that we'll be writing in the future would be big of n and big of n respectively. Yeah. Now, as we are completely familiar with the approach and the complexities, we are good to write the code. Let's start writing the code. So let's start writing the code. Just come to the compiler here, one compiler. So yep. Now we'll be making use of the fast input and the output. Along with that, we will be making use of the different utilities as well, right? Let's import these two actually. Java input output dot star, and also let me go with import Java dot util dot star. So this is fine. Next, let's go with a public class main. So this is fine. Uh, Let me go with main here. So this is fine. Yep. So within the main class, so let's initialize certain things, man. Yeah, first. So let's initialize n and this one count. So n is nothing but the number of vertices. Let's go with the count, unique canonical ID counter, right? So this is nothing but the counter you can consider. So I'll just go with static here, int n comma counter cnt I'll consider. So next, let's go with the degree. Degree of I is nothing but the degree of vertex I. So let me go with here static int degree. Yeah, so this is fine. Next, we need the adjacency list for the tree. Nothing but this will be one indexed actually. Just remember this one. So I'll just keep here static array list actually of integer. So this is fine. Static array list of integer. This is fine. Let me go with the yep. The next part, let's go with the hash map. So this basically maps the canonical string to the unique integer. And also we need one more this thing hash map for the memoization. Two more this one two hash maps here. One maps the canonical string to the unique integer and another one for the memoization node comma parent to the id, right? And we'll be making use of the hash set as well. This one set of the distinct root encodings. Yeah, so these three things we'll be making use of. So I'll just go with the static here. So let me give hash map let me go with the string here. So this one will be integer. Yep. So this is fine. Let me give this one capital I here. So map. So this one will be new. Let me go with the hash map. Yeah. So let me copy this one entirely. Paste it over here. So this one will be instead of MP. I'll just change this one to the F actually, the only thing. So instead of the string, let me change this one to the long here, right? So long and integer, this is fine. This works actually. Next, let's go with the hash set. So we'll just do the same thing here. Instead of the map, let me do one thing. I'll just give set here. So this is fine. So hash set so distinct integers, right? So I'll just make this one, change this one to only integer. So let me change the variable name to answer here, right? So here also let me change this one to the hash set instead of the hash map. So this is fine, man. So we are done with the initialization part. Next, let's do one thing. Also, let me leave space here. Yep. so that this looks good. Yeah. So now let's do one thing. Let's go with the DFS helper method. Yeah. So we'll be going with the DFS helper method that returns the canonical ID for subtree rooted at X with a parent P. Yeah. Let me give you a static in DFS. This is fine. Let me go with the parameters X and Y. So within the parameters, so within the helper method, the first thing is let's go with the key actually here. So key equals, I'll just go with the long. So this is fine. Uh, X left shift 20. So this is also fine. P. Yep. So this is fine. Yeah, so this builds a unique long key from X comma P. Yep, this is fine. So this is safe as n is less than or equal to whatever the value that they have given in the constraints. Yeah, 20 bits is greater than 10 something, the value that they have given here. 1 second. Yeah, this value actually. Yep, so this is fine. Now, let's do one thing. If the computed value before return the cached ID, then we have to get the key, right? So I'll just write it in this way. See, if f dot, let me go with the um, contains key here of, let me pass the key here. So this is fine. Let me return, let's return dot get of. So let me go with the key. So this is fine. So the next step would be we have to store the IDs of the child subtree. So let me go with here. Just give me a second here. I'll just go with array list of integer. So this is fine. So let me give capital I here. Integer. So let me go with the IDs equals mm, new array list. So this is also fine. So the next step would be for int y of g of x. So this is also fine. Let me go with a simple if condition here. If y equals p, let me give the continue. Let's make use of the continue keyword as we need to skip. We have to skip the parent to avoid going back, right? So also we have to calculate and collect the child's canonical ID. So I'll just make use of IDs dot add of let's recurse here DFS of y comma x. So this is fine, I believe. Yep, let me come out of this one entirely. Now, so we have to sort the child IDs to get the canonical order. So let me go with collections here. Dot sort of, we have to pass the IDs here. This is fine. After doing that, so let's build a canonical string representation. Let me make use of the string builder. Yeah, so this is fine here. SB equals new string builder. So this one, let me complete the syntax here. So this B has to be capital man here as well. Mm, yep. So this is fine. The next step. So let me append opening parenthesis here. I'll just go with append of this one, opening parenthesis. Yeah, this is fine. So let's go with the for loop here. We have to append the child IDs separated by the commas. So let's move on with the iteration. So this one will be int ID of IDs. So this is fine. String builder dot let me go with the append. So this one will be ID. Yeah, let me go with append again. So let me give comma here. So this is fine, I believe. Yep. So finally, string builder dot append. So this is fine. Yep. Yeah. Now let's do one thing. Let's go with a this one. We have to go with the final canonical string for the subtree. Yeah. So let me make use of the variable code, which is of the type string. Let me give sp dot to string actually. Yep. So this is fine. Yeah, let me scroll a bit so that we can see clearly. Right. So let's go with the map or let's map the new canonical string to the new integer. So I'll just go with simple if condition here. Map we have considered MP variable MP, right? So I'll just go with the contains key. So this is fine. Of let me pass code here. is also fine. Let me make use of the put operation that is provided by the hash map. Also, let me pass the code along with the count. This is fine, I believe. Now, let's get the integer ID for this canonical form. So this one will be int result equals dot get. So this is fine. Let me pass the code. Also, let's do one thing. Let's memoize for x comma p. So this one will be f dot put key as well as the result. Yeah. So finally, let's return the canonical ID. So this one will be return result, return result. Yeah. So let me come out of this one entirely. Now let's move on with the main method, man. So this one I'll just give main, remove this one also. Let's do one thing. I'll just go with the throws exception. So within the main method, as usual, let's go with the input output part. First, let me go with buffered reader here. So I'll just go with the BR new buffered reader of this one. I'll just go with a new input stream reader of system.m. Yep. So this is fine. The next one is we have n, right? So this one we have to parse, I think. Yep. We have n here, number of nodes actually. So this one will be integer dot percent of buffered reader variable br buffered reader dot I'll be making use of the read line. So this is fine. Yep, we are just reading the number of vertices here or number of nodes here. Next, let's go with the adjacency list from 1 to n. So I'll just assign g to new array list of n plus 1. Yep, now let's go with the degrees from 1 to n. So I'll just go with degree equals new int of n plus 1. This is also fine, man. Now let's initialize the adjacency list. So let me go with a for loop here. So this one will be int I equals 1, I less than or equal to n. Let me increment the I. So this one will be g of I, g of I. Let me assign this one to the new array list. So this is also fine. Yeah. Now let's move on with the this one, another iteration. So we have to read the n minus one edges as well. So they have given here n minus one edges, right? So see here, this one, 1, 2, 2, 3, and 2, 4. So we have to read the n minus one edges, all the edges. So let's go with one more for loop here. Int I equals 0, I less than n minus 1. Let me increment the I. So within this for loop, so let's split the line into two integers. We have to split the line into two integers. So I'll just go with string here. So this is fine. We consider variable s buffered reader dot read line. I'll just make use of the split. Actually, we need to leave the space, right? So let me leave the space here. After splitting the line into two integers, let's go with the first endpoint as well as the second endpoint here. So let me consider int u equals here. Let me copy the same thing here. This one. Yep. Integer dot percent. Let me copy this one. 1 second. Integer dot percent of this one. Fs of 0. Yeah. So let me copy the same thing here. Let me paste it over here. This one has to be v, and let me go with 1. Yep. So this is fine. We have successfully went with the first endpoint and the second endpoint, right? So next, let's do one thing. Let's add the v to use adjacency, and let's add u to the v's adjacency. Let's do these two things, and finally let's increment the degree counts. Let's do these three things. Yeah. So this one will be g of u dot add of v. This is fine, and g of v dot add of u. This is fine. We have to increment. Let me consider here degree of u. We have to increment this one as well as degree of v. Let's increment this one as well. Yep. We have successfully incremented the degree counts as well. Yeah. Along with adding v and u to the use as well as the v's adjacency. Yep. So let me come out of this one entirely. Now we are left with only one thing. So for every vertex I, we may attach new leaf only if the degree less than 4. Yeah. Uh, all we have to do is we have to compute or calculate the canonical ID for the tree that is rooted at I. Yeah, let's do that one first. So I'll just go with for here. I equals 1, I less than or equal to n, I plus plus. Yep. So within the for loop, if degree of I, if it is less than 4, if it is less than 4, then what we need to do here, we need to compute canonical ID for the tree that is rooted at I. So this one answer variable or the resulting variable we have considered ANS. Let me make use of the add operation. Let me make use of the DFS helper method that we have written already. So let me pass here I along with the root. We have to start from the root, nothing but the 0, from 0 actually. This is fine. Yeah, let me come out of this one entirely. We are left with only one step, nothing but we have to display the number of distinct canonical IDs, nothing but the answer. That itself is the answer, right? So that itself they have asked to find in the question, right? So within the question. So I'll just go with system out println here. So let me pass answer dot size. Yep, this is fine. So we are done with the coding part, man. So before checking the code with the different examples or the inputs, let me copy paste the signature starter template. So I'll just come here. Let me paste this one over here. Let me come to the question. Let me copy this one. The output that we need to get here is 2. Let's check the same. Hmm, cannot find the symbol P. Didn't we initialize the P or this one? Where is this actually? Line number 32. So we have considered int x and y. One second, just give me a second here. So this one has to be p actually. Instead of p, I have considered y here. So that is the reason we are getting error. So let me run this one again. Yeah, we are getting the output too. You can just ignore this one. What do we call? Warning actually. This is fine. Let me copy this one. The output that we need to get here is 1. Let's check the same. So we are getting the output 1. We have the final input here or the example. We have to get the output 3. Let's check the same here. Let me run this one. So yeah, we are getting the output 3 here, right? So let me copy this one entirely, the code. I'll just hit the submit code button here. Within the submission part, let me paste the code. Let me select the question here. D actually, Andrew and the chemistry. Let me hit the submit button. I hope this works for all the test cases, man. Let's see. This has to work actually. Let's see. So we have went with a this one tree hashing along with the DFS. Actually, you can clearly see here in the toast it is showing accepted. The verdict that we got here is accepted, right? So uh, we have went with a pure tree hashing here. We are making use of the hash map as well as the hash set along with the DFS. We are performing DFS as well. Basically, we are going with the tree hashing along with the DFS to solve this particular problem, right? So we have successfully solved the problem. I hope the solution part is completely clear, man, along with the approach and the complexities. For now, this is it. Thanks for watching, guys.